Hello everybody, and thanks for coming. My name is Alessandro Alinone, and I flew here yesterday from Milan, Italy. And even if I still have a 9-hour jet lag, I'm very excited about being here. And I hope you are excited as well, as we're gonna show and discuss some techniques that should make your lives easier when developing engaging real-time multiplayer games and online collaboration tools. So I am the co-founder and CTO of Lightstreamer, which is a global leader in real-time data streaming solution. What we do basically is to provide a server which has been optimized for 13 years now for streaming bidirectionally real-time data through web protocols, that is HTTP and more recently WebSockets. Now I guess that most of you are already familiar with WebSockets. You've probably attended our talks or you read articles or probably played with them either directly or through some frameworks like Socket.io or Sock.js, Primus, etc. So how many of you have at least a bit of familiarity with WebSockets? Come on, raise your hands. Okay, cool. And how many of you have some working prototype or even a live project using WebSockets? Okay, cool. So it's the right people to talk to. So what I want to submit today is that WebSockets are great, very easy to use, but they're also very risky because WebSocket is just a transport, a handy transport. But if you don't use it the right way, you risk to clutter the network and to create a bad user experience instead of providing a good gaming or collaboration experience. So what? Well, basically, you need to create a full stack of abstractions over WebSockets. Why? You have two goals, basically. You want to optimize the actual data delivery. That is, you want to reduce the bandwidth and to reduce the latency, which is something that is, of course, not managed by the very protocol itself. That's something that you have to implement yourself or through some framework on the top of the actual WebSocket transport. And the second goal is, of course, to simplify your life by using simpler, higher-level abstractions, so not working at the socket level, in order to increase the robustness of your code and make it really simple to develop something that works very well. So what is the perspective that I'm trying to bring here today? My background is in the financial services industry. So I've been working many years with banks to optimize the transmission of real-time data to online stock trading consoles. So my idea is that we can reuse the same exact mechanisms that we originated in the past 10 years for the financial trading applications and apply them to HTML5 gaming and collaboration in order to increase the quality of the data delivery. So these are just some names of banks using our product for this kind of data delivery. So during this talk, the demos I will show are based on Lightstreamer, but the underlying theory and techniques have general validity. So you could implement them yourself in your own real-time web stack. So I need your collaboration now. So please take your smartphones, laptops or tablets, open whatever browser you want, and please go to this URL. Hoping that the Wi-Fi works, because it seems to be quite crappy today here. But let's cross our fingers. So what you're seeing here is people logging in the room, or even somebody. Oh, it's on the bottom, bit.ly/more888. I couldn't make it shorter than this, but I tried. Okay, so anybody of you logging in is appearing here on the screen. And what you see here is some sort of a chat, so the very basic collaboration model. You can also see that you are typing in real time, so character by character typing from your phone, and the messages appear here. So it's many of you, and I'm afraid that I cannot show everybody of you on the screen. If I reduce the zoom level, it reflows, but you cannot read it so well. So these are very basic initial examples where WebSockets are used underneath, or other web transports in case WebSockets are not supported by your browser. So there's some transparent fallback. And it's a two-way collaboration system, basically, because you receive the broadcast of all the other messages, and you can send and type messages yourself. So when we talk about the so-called real-time web, which is a buzzword that has been around for some years now, well, you must know that the first instance of the real-time web dates back 15 years ago in the financial services industry, because the first stock trading solutions had HTML front ends that could update in real time. Now, of course, with HTML5 and WebSockets, there's a completely brand new wave and revamp of real-time collaboration. But now everybody tries to use WebSocket inside their application, incurring the risks I mentioned before. So what I want to show you now are some techniques you can use to make WebSockets really work in the real world and not just in a test environment. So now let's imagine that this kind of collaboration interaction is not enough and you want something that goes towards the direction of actual games. What you have to do now is first cross my finger, and second spell the magic word, which is abracadabra, and you find yourself in the room. I see now that the screen is compressed from 69 to 4:3. Is it visible in the place? Or? Not so good. But okay, so I hope you were able to see where you were before going into this map. And what you can do now is use your phone either with the sensor, so the accelerometer inclining to move your person, or switch to the keyboard-based keys in case it doesn't work to move your own. You want me to switch back to the tile so that you can see where you were? Okay. The wire, the mic?
Yeah.
Okay. No, but it's okay. It's okay. I go on like this. Okay. Cool. So sorry. If you see yourself, okay, keep reflowing. Okay, I switch it again. Up. And then increase the size. So you see here that the degree of interaction is higher, of course. Now you can move in a bidimensional world, and you can control what you're seeing on screen by your own devices by connecting through the internet. Let's go up again. Okay. So now, let's imagine that this is not enough. You can still keep chatting and typing your messages which appear under the person itself, etc., etc. Now, what happens if we throw a ball in this world? Here it is. Okay. You can start playing with it. Actually, there's too many of you. I didn't expect so many people. It's difficult to play. But you can see that what is implemented here are both collisions among the players, because you can bump into any other players and move it a little bit. And full physics of the ball, because the ball is able to bounce It has accelerations, decelerations, and all that is needed to make it a bit real, actually. So you can imagine how complex could be the game loop in this case, even if the visual representation is really very, very basic. But with this kind of real-time interaction and the implemented physics, it's not something so simple you can imagine. So let's have a look at the game loop, the JavaScript game loop of this HTML5 application. So I go back to the slides for a moment. You see here. Here you go. This is the inner loop of this game. Why is it so simple? Because the physics run completely on the server side. In this case, the client is a dumb renderer. It keeps receiving the stream of real-time coordinates of all the objects in the world, and what it does is just to move a div. You see here we have a callback on item update. We receive this object update. We extract the x coordinate and the y coordinate, and we simply change the position in the page with a simple calculation in order to center it based on the upper left corner, etc., etc. And when you're playing with this stuff, the only code that is executed is this one, apart from the other part of code which sends your own movements to the server. But this is the actual game loop based on this kind of updates. So it's a case of full offloading of the physics to the server and the use of the WebSocket transport for the actual delivery of the positions. Let's spend a couple of words on the different models for multiplayer games, actually. So the first model is what we call pure server-side. I'm showing an extreme scenario here, which is the one implemented by this demo we just used. A scenario in which the physics run completely on the server side. So the client has no notion of physics, no game engine at all. It's just a renderer. So what happens is that the slides are really bad compressed this way. In any case, can you read it in any case, even if it looks bad? Okay. So what happens is that you have your real-time server, and the clients keep sending commands to the server, where commands is the user input. For in this case, the keys that were pressed, or the movements detected through the sensors of the device. So you have streams of commands sent from the clients to the server, and in the opposite direction, you have a stream of positions. For each object in the world, you receive the real-time position in order to render it in the new place. Position are usually coordinates, quaternions in case of a 3D world, and what you need to bring the visualization on the client side. On the other hand, we have another extreme scenario where it's a pure client-side mode. In this case, the physics run only on the client side. So your game server does not have a representation of the world. Your real-time server is only used for dispatching the real-time events to your clients. What happens here is still that all the clients send their own real-time stream of commands to the server. And in exchange, they receive all the other real-time streams from all the other players in the world. So in this case, the client has to process all the inputs. Every client has to process all the inputs for all the players and create its own representation of the world. Of course, as always, the truth stays in the middle, and so the most widespread model is the hybrid mode, where the physics runs both on the server side and the client side. In this case, you have all of the components shown before. So you send the commands to the server, you receive all the other players' commands, but you also receive some low-frequency updates to the actual positions. This way, you can resync with the authoritative game server which keeps the actual real state of the word in case the client words diverge. When you send this low frequency position, you still send the coordinates and quaternions. When you send the other commands, you have two sub-models here. You can choose to send just the basic level input, so which keys were pressed, how you move the mouse, etc., or just do a bit of processing on the server side to refine this data before sending them back. In this case, you're probably going to send a velocity vector or an angular momentum vector, etc. So you have both of the models that can be applied to this. What are the pros and cons of the different model? The pure server-side mode, I show you the inner loop of that demo, is really simple. You can create a very simple client-side code which can run on cheaper client hardware, because you don't have to have the physics engine on the client side, but you must also be able to move some divs, or better, to use some WebGL implementation to move 3D objects. The cons is that it can potentially use a lot of bandwidth. That's why you risk to clutter the network with WebSockets. And the degree of animations, how smooth the animations are, is fully dependent on the latency that you have on your network. So if you have network congestion and a high latency, what happens is that you're not going to see these players move smoothly, but in a more with less frames per second, basically. Pure client-side mode, on the other hand, has the big risk, the risk so that words can diverge. Imagine each word processing its stream of inputs, but depending also on a lot of local variables, like basically the speed of the clock or some interruption from other applications. So it's impossible not to make client-side words diverge and so have different game representations as part of different clients. But of course, the pros is that doing all the calculation on the physics on the client side, you can have smoother animations and more reactive animation, and also can use some techniques like prediction and interpolation, which are even more possible in the hybrid mode, because you have all the elements for doing your local calculations to improve the animations, but also to periodically resync with the authoritative server. But the hybrid mode is a bit more, or much more complex to implement, even if most of the games, even outside of the HTML5 world, tend to use this model, basically. So I want to go on with the experiment and try something that I'm not sure if it's going to work, but it's the only way to show from a pragmatic way what I'm trying to explain. So I'm launching a second instance. Let me put it in a side window if I can. Side to side with this one. Let's reduce. Where is it? Sorry, guys. Okay. Okay. So, I don't know if you... Sorry for using Windows. So, you can see here underneath the actual bandwidth which is being used by these words. So here, I don't know if you can read it, but in this moment it's using approximately 120 kilobits per second, which is something like 15 kilobytes per second to the left. To the left is the good word, with all the optimization techniques that I'm going to discuss later. To the right, we are simulating, we are quite ready to simulate a typical WebSocket server. You're probably used to something like Socket.io or Sox.js or any other typical WebSocket server, where data is not optimized on the fly depending on the network condition. So right now, the bandwidth is a bit smaller, but not so much. And in both the cases, we have unlimited kilobits per second. What I'm gonna do now is to simulate network congestion. So I reduce the actual available bandwidth on both the clients. And the two words that now are fully synchronized, we want to see how evolve, basically. So, for example, let's reduce the bandwidth to 40 kilobits per second in this word, and the same in the other word. Okay. If Chrome assists me, otherwise I have to reload the window, because it's just a rough prototype. Okay, let me reload. This is unfiltered. Okay, sorry, to the left was unfiltered, and to the right was the optimized way. So let's go here. So to the left is the typical WebSocket server. Let's go to 40.5. And to the right, everything is hanging. Okay, keeps going back. Let's see if it's able to process the events now. Okay. So it keeps going back. As an apology, consider we developed this stuff in the last 3 days, so, you know, let's try again. So what should happen, basically, if if the GUI wasn't so heavy due to the optimization on the visual layer we didn't implement, is that if you reduce bandwidth a lot, you still see on the right, which is the optimized word, you still see your person moving in real time, even if a bit less smoothly. What happens to the left is that you see a slow down playback of the same word. That's why, because you're not able to send the full data flow at full speed, and the server keeps queuing update and play back them slowly based on the available bandwidth. So if you're able to sample, and now I will show something more about that, if you're able to sample, basically, you can still keep a real-time synchronization of the words. If you don't resample on the fly, which is what any typical WebSocket server isn't able to do if you don't implement some specific mechanisms on the top of it, you will see this slowdown. So I'm happy to see that we were able to reproduce it, because it's the first time we try with so many players connected. So now that I gave you a practical idea of what I mean by slow down of the word without resampling, let me explain something more specific. So one of the big debates in the gaming world, as you probably know, is TCP versus UDP. But we are in the HTML5 realm, so TCP is the way to go, apart from WebRTC, which is still early and focused on client-to-client peer connections, not typical game server connection to the clients. So what are the pros of TCP? You know, TCP is reliable. It guarantees the in-order delivery of your data. And the other pros is that if you use a web protocol on the top of TCP, that is HTTP or WebSocket with all the fallbacks, you can even pass through any kind of proxy and firewall. But the cons of TCP, again, is in its reliability. To be reliable, it needs to retransmit segments when they're lost. So when a segment is lost, you keep queuing up new data in the buffer until you are able to deliver the initial segment. And this provokes a clutter of the network because you keep sending bursts of age data. You already have some network issue, you increase the quantity of data that you're sending because your producer, the game engine, continues to produce this high amount of real-time data. And you could trigger an even worse packet loss, especially on small bandwidth networks. That's why most of serious game developers like consoles, etc., tend to use UDP instead of TCP. What I want to discuss today, or to show today, is that by using some techniques, as I said before, the ones originated for financial trading application, well, we could make even TCP quite usable for some nice HTML5 games. So let's talk a little bit about these possible techniques. I already mentioned this. You need to resample data. When you produce a lot of data, you can queue them up and try to deliver them based on the availability of the network, or try to resample the data flow on the fly. Consider that in many cases, you don't need all of the samples. If your game engine works at 100 Hertz, it produces 100 positions per second, and you want a smooth animation, you only need 30, 33, 25, or whatever, depending on the kind of quality you want to give. But even if you're not able to deliver 30 updates per second, and you can only send 10 updates that are fresh and real-time is much better than sending 30 that arise from the past, okay? Because reducing the amount of data that you deliver does not mean sending old updates. This is how resampling works. But resampling is not an easy procedure. It's an algorithm that needs to take in input several variables. The unsampled data flow, of course, the desired maximum frequency, which is how many updates per second you would want, the desired maximum bandwidth, because you may want to put a cap on the bandwidth you use. If you host your game server and you pay for the bandwidth you're using, you could decide that you don't want to use more than 50 kilobits per second per user, whatever is happening in the world. So if the bandwidth goes above that limit, you want to start resampling and never exceed. This allows you to tune your system and know in advance how much bandwidth you need based on how many users you have, independent of what the users are doing. And finally, the most complex part, you need to take into account the currently available bandwidth. And you can do all this stuff by some sort of dynamic throttling. Dynamic throttling means that for each update that you need to send, you decide whether to send it or to discard it based on the actual availability of the connection. So you have to know somehow if you have a congestion or not. And the best way to do that is to keep a small TCP buffer and see how fast you can empty it, because you can empty the buffer only when you receive the acknowledges back from the other side. And that's a good way to know how the network is behaving moment after moment. What you have to do with your streaming server is to combine heuristically all these parameters, and at every moment decide what to send and what to discard for throttling. Throttling is better with conflation. Instead of simply discarding some events, you may want to try to merge them as much as possible in order to lose less information. Simple example. You have 3 events produced by your game server, the 3 coordinates. Event 1 sends all of them. Event 2 has unchanged on the X, and event 3 has unchanged on the Y. Now let's suppose that your resampling algorithm decides to drop event 2. So instead of just dropping it, it's smarter if you conflate event 2 and event 3. So you will send event 1 and a resulting event from the conflation on 2 and 3, where you keep the X for 3, the Y from 2, and the Z for 3, because it's fresher than from 2. This is conflation. And again, it's a technique that has been used for many years in stock trading application. When you have the typical ticker or matrix of prices that keeps updating in real time and only a field change. You don't want to lose it if it doesn't change in the next event. You keep carrying on its value until a fresher value is available to override the previous one. And why not apply this to gaming? There's a perfect fit together with the dynamic throttling, of course. Well, another technique to use regards the low-level TCP. First of all, you have to absolutely disable the so-called Nagel's algorithm. Nagel's algorithm is the algorithms of the TCP/IP implementation of every operating systems that keeps waiting for more data to be produced in order to forge larger packets. But this introduces some latency that you might want not to have in a real-time game or real-time collaboration system, basically. So you have to try to pack your data efficiently in TCP segments. You can do let the operating system do that, because the operating system doesn't know how your game behaves. So it's up to you to decide the overhead between how much latency you're available to accept and how much you want to create larger TCP segments in order to increase and optimize the data flow, because the smaller the TCP packets and the higher is the overhead on the CPU, on the network, on the CPU, the server, on the network, and on the clients. But if you wait too much to collect more data to forge a larger TCP packets, of course, you are delaying the delivery of the original data, so you're increasing latency. So this is a very important topic. Decide your trade-off between latency and optimization. You're available to apply a 30 milliseconds delay on all of your data. Good. It means that you can wait 30 milliseconds in order to collect more data and send a more efficient TCP stream on the network. Okay, time for some more fun. I give you another URL, but this time it's probably not going to work on smartphones. You probably need a good Chrome, so if somebody who has a laptop, or if you want to try with the phone in any case. And I go myself to that. It's bit.ly/more777. I can close this one. Again, who are you, Alessandro? Again, let's cross our fingers. Oops. Sorry. Let me reopen it. I destroyed the surprise effect. But you know, this is how demo works. So what you already saw here is the super famous Super Mario Bros. Original implementations from the 80s. So we found some code built by a great guy some days ago, and I felt in love with this HTML5 implementation, and I told my team, we must make it multiplayer. And it and it took it just 2 days of work to create this prototype, which is absolutely not perfect, full of bugs, but still gives you an idea. So if I start moving myself, I find all of you following me or preceding me with all of your names, and and again, this is pure HTML5. So we are not interacting one with each other. Everybody's playing in their separate world. Oops. And what we're seeing here is just one word for each player displayed on the top of the other. So each of you have their own interactions. So is anybody using cell phones? Is it working? Ah, cool. Game over. Oh, okay. We also try to implement this simple accelerometer to try to move it, and the keys to jump, etc., etc. So what's the purpose of this apart from fun? To demonstrate that it is possible to use TCP for games and it could also be very easy if you use the right abstractions, because as I said, it was a very low effort. Let me show you. It's fun, but let's dig into the code. So let's stop the fun. And if I can find my... I closed my slides, sorry. Oh, God. It's the worst error I could do. Okay. And now we have some background music. It's quite nice. So let's go to where we were. Okay. Sorry. Here we are. So I show you some of the key code that we added to the original implementation of this game. So what implementation model did we use based on the model I showed you before? This is a hybrid approach. What we do is to send the local Mario's commands to the server. But at the same time, we are piggybacking the current positions in order to correct the drifts on the other clients. In this case, the physics engine, game engine, runs completely on the client side. So the server doesn't know anything about the Mario world because it was created as a single player game, so all the logic is on the client side and we didn't want to port it on the server side. What we do is to send the authoritative position of each Mario together with the commands that the user is putting as input at that moment. So you can see that there's a key down. We use this function to send an event, key up to send an event, so that we trigger all the key presses. And this event is very simple. We just use our library to send a message, which is made up of the key that were pressed, up or down, and the current position of this Mario, so that all the other Marios receive the positions of each one and are able to correct the predictions that they made based on the commands they received. So this is the loop that sends the commands. Now, let's see how you receive remote Mario's commands from the server. Again, you subscribe to some kind of data. You added a listener to receive the real-time callbacks. And for each update, you extract the user and the status. Oh, this is the loop to manage the multiplayer part. So players coming into the world and leaving the world. So not the position, sorry. In this case, each time a new Mario enters the world, you receive an add command with the username. Every time a Mario leaves the world, you receive a delete. And if you receive some updates on their nickname or other information, an update command is received. So based on these simple callbacks, you know in real time how many players you have, and you can manage not only the positions in the game, but also players coming into the game at different times and leaving the game at different times. Because one of the other issues I haven't mentioned before, but it's very, very strong, is how to manage the initial snapshots of the world, how to manage the initial synchronization of the different worlds, so that anybody starts from the same state of the world in that moment, even if they enter the world at different times. And finally, the loop that manages the remote Mario's command. So in this case, I receive an event from the server containing the position for one of the other Marios. And I'm gonna move my current representation of another Mario to the authoritative positions with just these two lines of code, basically. And at the same time, I extract the involved keys, the commands they pressed, so that I can do my client-side predictions of the next moves of Mario's, and make it move before I receive the actual authorities positions from the server. So we have a specific case of an hybrid model, which took less than 2 days of work to implement. Again, I said it's very imprecise, but it's playable, and you can go on. You have all the other levels, etc. And we'll put it online soon. This leads to the discussion of other techniques that you should want to implement to get this easiness of implementation together with the optimization, which are delta delivery and the use of lightweight messages. Delta delivery means that you don't want to send a full snapshot of your game world for each update. You only want to send what has really changed. So if your game server, your physics engine, produces a full snapshot for each cycle, what you want to do is to compare it to the previous output and only extract the changes, and then only send the changes to the client in order to highly reduce the bandwidth that is involved. You only need to send full snapshots at game startup, of course, and upon disconnections. So if your browser disconnects and loses some commands, when it reconnects, it needs to retrieve an initial full snapshot of the world in order to resynchronize, and then from there, it can start receiving the new deltas. In other important aspects, I see a lot of implementation using JSON to transport messages to the client side. Well, I don't think that's the right approach, because JSON is too verbose and too redundant. It means that for each single update, you have to say, this is the X, this is the epsilon, this is the X, this is the Y, this is the Z. You are carrying a lot of unuseful metadata that increase the bandwidth a lot, not to mention XML, of course, which is even worse. So what I submit here is that you should use a position-based protocol. So you must subscribe in advance to the fields you're interested to and only receive the pure payload without the redundant metadata, which is typical of JSON. Of course, especially for high frequency, high bandwidth applications, but games are probably one of the highest bandwidth real-time applications that we know about. So you should take into consideration this kind of optimizations. And finally, you should also consider the correct choice of the transport. I mentioned at the beginning that WebSockets is a relatively new standard, but it's quite widespread now, but not so widespread that you can use it universally. Apart from older browsers that don't support it, the real pain is with firewalls and proxies and network intermediaries that don't speak WebSocket and they block it. There are some mobile operators that does not allow you to use the WebSocket protocol. They only allow HTTP. Apart from the encryption, if you use encrypted WebSockets, WSS, then in most cases you're able to make it through. But encrypting data for games only to pass through proxies and firewalls adds of course, more heaviness to the whole thing without a real purpose. So what should be doing is to have some fallback mechanism. So if WebSocket doesn't work, you have to switch down to HTTP streaming. Even if HTTP streaming doesn't work, you have to switch down to HTTP long polling or smart polling. You know that HTTP streaming is as efficient as WebSockets in sending data from the server to the client. I should have a slide for it. Let me see. Yeah. Look at here. You see the same kind of interaction between the browser and the server using WebSockets and using HTTP. So the green arrows are for sending messages from the client to the server. The red arrows are for sending messages from the server to the browser. With HTTP streaming, you don't have any difference in sending message from here to here between WebSockets and HTTP. And this is contrary to common belief. The real advantage of WebSockets over HTTP streaming is only in client-to-server messaging. And I try to say this every time because I always find the common belief that is the contrary. WebSockets are more optimized than HTTP for streaming data from server to the client. No. If HTTP streaming works, it has exactly the same overhead than WebSockets. HTTP long polling is another topic. It's much less optimized. A question? Yeah, okay. We have the question. I couldn't understand, sorry.
I can't hear you?
not very well. Or if you can wait, we have the question and answer session in a few minutes. So we are close to the end, so just keep the question there. And when you need to send the messages from the client to the server, if you use HTTP, you need to do a full round trip for each message, because HTTP pipelining is only implemented in some browsers, not the common practice. While with WebSockets, you have real asynchronous bidirectional communication. So my message is, when you need to send high-frequency updates from the client to the server, you really need WebSockets. If you only need to send high-frequency messages from the server to the client, WebSockets are for sure nice, but are not so vital. You can do the same exact stuff with HTTP streaming. If I go back to my demo, if I zoom enough, not here, let's go to the other one for a moment. I show you this guy here. This guy here is an indicator we put to say what connection we are using. It's written connected over WebSocket in streaming mode. But if I add the proxy here that blocked WebSockets, I would connect automatically in HTTP. And if streaming worked, you would assume the same quality of movements for the players, even if WebSockets are not working. This is what we call the stream sense, the ability to decide the best transport on a per-client basis by detecting what the client is really able to do based on the kind of connection it has. We have 5-10 minutes, so let's show the last stuff. It's a bit more complex, so I just give you a hint. This is already online, so you can play with it directly. This is the 3D demo, which is what I explained in an article I recently wrote. I will give you the link later. It's a bit more complex because we try to put together all of these concepts and gives you all the leverages, the slides, and the buttons to tune the data delivery as you want and to experiment and see how much bandwidth is actually being used. Let me zoom in. So, it's some nice stuff. What we do here is the rendering of the 3D virtual world, very simple, of course, using the 3JS library, which underlies use WebGL, etc. We are not the graphic guys, we are the delivery guys for real-time data. But the concepts is what I'm showing. Okay, a lot of you connected, okay. Let me go to a new word so that you don't disturb me in my experiments. So now we are in client-side mode. So client-side, as we said, means that the physics is running here locally. I can move a little bit just to start. And what you see here is completely managed on the client side. But we have the periodic resynchronization. So every 2 seconds, the server sends an authoritative snapshot of where all the objects in that word are actually positioned. Now here you can play in switching to server side. You see that in client side mode, I'm using no bandwidth at all, only some heartbeats to keep the connection open. If I switch to server side mode, now you see the same smooth animation, but all the coordinates are coming from the server. In this case, the client is a dumb renderer. The server says, move this object to this position with this rotation, etc., sending the full quaternions. If I open the matrix, you can see the real-time data that is being received from the server. So this change in data is traveling on the network, actually. Is not produced on the client side. And we're sending the 3 positions and the 4 quaternions for rendering the 3D objects based on the server calculations. Now, what I can do, apart from having some fun with binary string, double precision, single, etc., is to work on the maximum bandwidth and maximum frequency. Now I have 33 updates per second. I can resample it on the fly, and let's say I want only 8 updates per second. So I sent a message to the server telling the server to start resampling at 8 updates per second. You see that it's decreasing here. And you also see here that it's less smooth movement. Let's go down even more. Let's go down to 3 updates per second. And you see that 3 updates per second are respected. With 3 updates per second, I'm using 3 kilobits of bandwidth. If I go up to something like unlimited update, let's say 80 updates per second, the bandwidth increases to 105. Oh, somebody entered the word. Welcome. You're this guy. Okay. And as a final experiment, but it is even too much hard. I'll try, so if it doesn't work, I'm sorry. This server I'm connected to is on Amazon here in the California zone. I want to try to connect to the same demo living on a server in Europe and show you how the latency of the link impacts on the quality of the animation and how the algorithms try to compensate the higher network latency because the server is more distant. Let me try if it works. We're running out of time, unfortunately. So you can find it online on our website here, and here's the link. This is the European server. So I create, the words are different, of course, because 2 independent servers, but I try to recreate the same situation. So very quickly, server side, 33 updates per second, and I do an SD2 and the rotation, okay? And you see here that I'm using 8 kilobits per second. Now let me do the same exact thing in the other word. So let's enter a fresh room. And let's go server side, okay. It was 33 updates per second. Okay, and I did, it's already moving, okay, but a 2, and I need to add this, okay. It's quite similar in any case. So, I think you can already see it. Let me zoom in. Where basically, it decreases the quality, sorry. I don't know if you can perceive that this guy coming from Europe is moving at a slower frame rate than this guy coming from the local server. But if you don't see it, believe me, you can try yourself. But it's interesting to look at the bandwidth. The American guy is using 30 kilobits per second. The European guy is using 8 kilobits per second, with all the other variables on the client side and the server side staying the same. Why? The naive answer could be, well, because I have less bandwidth to connect to Europe. No, that's not the answer. The bandwidth, the available bandwidth is quite the same, or for this small number is quite the same. It's the latency that is provoking the use of less bandwidth, because having higher latency, I need to wait more before sending new packets since I receive the TCP acknowledges. And in this delay, I keep merging and conflating, as explained before, more data. The result is that I still keep the word in real time synchronized, but I'm able to send less amount of data. So the result is that the bandwidth is saved, but the application is less responsive and less smooth. If you used a typical WebSocket server without resampling, you would have the same experience. So you would see this guy moving at a slow frame rate, but using a much higher bandwidth, because you are queuing all of the updates and you send multiple position updates in the same TCP packets. If the client side doesn't want to introduce a delay in playing back them with the actual timestamps, we will only display the last position. So the result is that you have the same crappy game, but with much higher bandwidth. So if you have to provide a crappy experience, at least try to save bandwidth, basically. That's the... Okay, since we are close to the end, I need to do some commercials, sorry. So let's go to the final slide, okay. So Livestreamer implements all the discussed techniques and much more. No, it's our product is not open source, but free editions are available. And we also have a startup program so that we give away licenses to newer entrepreneurs for your own startups at a nominal price for 1 year. And make sure that you do the best things out of Livestreamer, leveraging the experience we bring from the finance, also the defense application, aerospace. Livestreamer is used by NASA for the web telemetry of the International Space Station, for example. If you go to the NASA site, you can see some real-time data coming from the International Space Station and delivered to HTML5 application, and a lot of other fun stuff. But we have run out of time, so I think we have a couple of minutes for questions. You can come to our booth if you have other questions. We are to the far right. It's number 36. Okay, please. Thank you. Thank you. Okay.
Question?
Yeah.
So WebSockets are great, but what about some of these newer specs that are coming out through the W3C, such as
WebRTC
and raw sockets?
Yeah. So
going forward, how will a web developer know how to choose?
Yeah, WebRTC still in the early stage, but gaining momentum. But its focus is a bit different for the moment. It's for peer-to-peer client communication. So before having a world where you don't need a game server, but you can only play peer-to-peer, it's probably not so near, not so close. What we're thinking about is to use WebRTC even to talk to the server so that you're able to use UDP in all the cases that you want. So it's certainly an interesting route in very, very early stages. So for developing serious stuff now, you should go with HTTP and WebSockets. But probably the future is...
The question was, how are you measuring the actual bandwidth? Are you taking the size of the body and then plus the header size?
Yeah, it was the full bandwidth on the network, including all the TCP IP overheads. So we count the size of the packets, we add the TCP IP in Ethernet headers, and that's the resulting bandwidth, which is available as a call to the server, actually, for each session, each connection. Okay. You had the guy had the question before.
Me?
Ah, sorry. Okay.
Well, so you said that WebSockets is better than regular HTTP for talking from the client to the server?
Exactly.
Why?
That's contrary to common belief, as I said, but that's the truth. Yeah, because when you stream data from the server to the client in HTTP, you do an HTTP request, and as part of the response, the server can keep sending data. After the initial handshake, after the overhead of the response in HTTP, what is traveling on the socket is pure TCP. The HTTP part finishes under the HTTP, after the HTTP header. But at that point, what you're sending on the network is pure HTTP. I could say something even bolder. WebSocket in that case is slightly less optimized than HTTP because you also have to send the metadata for frames and messages, while with HTTP streaming you just send the plain payload. On the other hand, when sending data from the client to the server, you cannot keep pushing high frequency messages in HTTP because you need to wait for the response, and the browser has full controls over the HTTP connection pools, and it even does you guarantee of the order. It could open 2 different sockets to send you your 2 HTTP gets or posts, and the first one could arrive after the second one. While with WebSockets, you have a single physical connection. You can stream from the client to the server. So I always like to say that from the server to the client, HTTP streaming with WebSockets is the same. A different discourse is HTTP long polling. Long polling is, of course, less optimized than WebSockets. Okay, you're not convinced?
So I don't know. I just going to mention that at so at a different convention, the guy did a talk on Meteor, and he said that they had decided to not use WebSockets but use long polling instead because it was capable of being zipped, like compressed.
We
Whereas
are able
WebSockets
to
was not?
No, we are able to compress even HTTP streaming, so we can gzip the response on the fly. But now a new specification we are working on with all the working group in the W3C is for WebSocket compression. It's called WebSocket deflate. So in a few months, this spec should be ready and also implemented in browser, so that we can also compress WebSockets.
Okay, cool.
Cool. I think I must. There's another talk now, or we have a break? Okay.
Yeah, 30 seconds if you have more questions.
Thank you.